Okay, now we're going to look at linearly independent sets and bases for subspaces, or for vector spaces. So we've already seen the idea of linear independence and dependence, where a set is linearly independent if the only solution to combining your vectors equal to 0 is the trivial solution. Linear dependence is when you have a solution that's not 0. So you have a way of combining your vectors without setting all your coefficients to 0, where you can build the 0 vector out of them. So we've already seen this idea. We're going to take it a little bit farther today. We're going to start with theorem 4. If we have an indexed set of 2 or more vectors where at least one of them is non-zero, so we can say that the first one is non-zero, then it's linearly dependent if and only if there's some vector in there that you can combine all of the previous vectors to get it. So in other words, linear dependence means that there is a vector in here that you can build from all the others. Now we've seen that idea already. This is restating it just a little bit to make it a little bit more precise, a little bit easier mathematically. The idea is that if you have V1, V2, V3, say V4, V5, and V6, the idea is that if you start at the front and keep going, at some point you're going to get that the next one can be built. So what it says is that you start looking at V2. Can V2 be built from V1? No, then that means that V1 and V2 together are linearly independent. Then take a look at V3. Can you build V3 from V1 and V2? No, then move on to V4. Can you build V4 from V1, V2, and V3? Yes, if you can, you're linearly dependent. And this says that you can just go along sequentially like this, and linear dependence means that at some point you're going to find a vector that can be built from all of the previous ones. Whereas before we had the concept that a vector someplace in there can be built from all of the other vectors. Well, this says you don't have to check all of the other vectors, you can just check the ones before it. And at some point you're going to hit a vector that can be built from the ones before it if it's linearly dependent. We've seen the idea of a basis. So a basis is a linearly independent set that generates your space. So in other words, a set of vectors is a basis if the set is linearly independent, and the subspace spanned by those vectors is the vector space you're interested in. That's a basis. We've already seen this idea. A standard basis. We have this notion of a standard basis when you're talking about when your vector space is Rn, is all of Rn. So a standard basis is the columns of your identity matrix. So this is denoted as E1 equals 1, 0, 0 all the way down. E2 is where you have the 1 in the second point, and so on. And EP is all of zeros, then a 1, and then the rest of it is zeros, and that 1 is in the pth row. All the way down to En is where you have your 1 at the bottom. Okay, this is called the standard basis. Okay. So we're not going to deal with that a whole lot right now. That's just to kind of let you know because we're going to be using that explicitly in some future lessons. But now we have theorem 5, which is this spanning set theorem. So this is gets one of the key properties of a basis. So if we have a set in a vector space, and H is the span of those elements. Okay, so you have V as your big vector space, you have H as a subspace, it's something inside it. Where H is built by you pick out a number of vectors from your vector space and you see what they span. It could be all of it, it could be a smaller set of it, of V. Okay, So H is the span of these vectors that you pick out. The theorem says a couple of things. It says, first off, that if one of the vectors in S is a linear combination of the remaining vectors, then you can take it out and you're still spanning the same thing. Second idea is that if you're not dealing with the zero subspace, then some subspace of those vectors some subset of those vectors you started with is a basis for H. So in other words, if this is saying if it is if you can build one vector out of the others, then you can remove that vector. And it's saying that if you're looking for a basis, you have it. It's some group of the vectors you already have. You don't have to look anywhere else. Your basis is there. You just have to find the right vectors. Now, in this section, we've kind of seen this idea before, but we're going to go through a little bit of a proof of it. Okay, it's not going to be a very detailed proof, but to give you an idea of why this is true. So, for part A says that if we have something that's a linear combination of the others, we can drop it. So what we're going to do first is we're going to rearrange the vectors in S if we need to, okay, so that the very last one is a linear combination of the ones before it. Okay, so we have some equation that lets us build the final vector from all of the others. And that's just we just do that for convenience. It makes the notation and the writing of it a little bit easier. So the idea is that the last one can be built from all the others. Now, what we're trying to show is that the span of the big set is the same as the span of the smaller set. The smaller set being where you drop that last vector. So how do you say that the span of something is the same? Well, what's the span? The span of a set of vectors is all of the linear combinations. So to say that the spans are the same, we're going to show that if we can build it from the first set, from the bigger set, we can also build it from the smaller set. In other words, the span of the first set, everything you can build from it, is equal to the span of the second set, everything you can build from it. So how are we going to do that? We're going to say, here is a vector that we build from the bigger set. And we're going to show that no matter what that vector is, we can build it from the smaller set. Well, this is fairly easy to do. We have that x is equal to C1V1 up to CPVP, but we have an equation for VP. So this is equal to C1V1 plus, I'm going to write CP minus 1 VP minus 1 plus CP. Well, now we can substitute for VP, A1 V1, and everything up to AP minus 1, VP minus 1. Take that and simplify it, and what do you get? You get an expression to build X from your smaller set. So in other words, everything you can build from your bigger set, you can build from your smaller set. So the spans have to be the same. What about part B? So for part B, assume that your set is linearly dependent. Okay. Otherwise, we're done, because remember, a basis is a spanning set that is linearly independent. So if it's linearly independent, we have it, we're done. So what about when it's linearly dependent? What do we have to do then? Well, from linear dependence, the first part that we just saw said that we can drop one of the vectors. Linear dependence means that there is a vector we can build, at least one vector we can build from all the others. So drop it. Part A says that's okay, we're still spanning the same set. So that means that we've met the first condition, that we span the set we're interested in. The second condition is linear independence. Well, this is fairly straightforward. Just take a look at the vectors that are left after you remove one and say, are they linearly independent? If they're linearly independent, we're done because it spans and it's linearly independent. If they're not, do it again. Drop another vector. If they're not linearly independent, it means that there is a vector in there you can build from the others. Drop it out. and try again. Just keep doing that until you do get linear independence. And at some point you're going to have to, because you come down, at the worst case, you would come down to a single vector. Once you have a single vector, it's linearly independent. So this is the idea of the proof for part B, that you can always build that basis. It uses part A and the fact that if you drop enough stuff out, eventually you will be linearly independent. Worst case scenario, you have to go all the way down to a single vector, but at some point, the vectors you have left will be linearly independent, and that's the definition of a basis. So as an example, here we have 3 vectors, and we're going to say that H is the span of those 3 vectors. These vectors are not linearly independent, so it's not a basis. Why aren't they linearly independent? Well, notice that V1 times 2 is equal to V3. So we have that right here. So V3 is a linear combination of the other vectors, of the previous vectors. So it's not linearly independent. But theorem says that, well, we have V3 is a linear combination of the previous vectors, so we can drop it out. Theorem 5 says that the span of the first 2 vectors is the same as the span of the first 3 vectors. So we have a smaller set now that spans H. That's equal to H, that span. So H is what we're interested in. We have 2 vectors that span it. All we have to do now is say, are they linearly independent? Well, you can see that those vectors 1, 1, 2 and 1, 2, 2 are linearly independent. 2 vectors, one is not a multiple of each other. That's enough to say they're linearly independent. So that's our second condition. We have 2 vectors whose span is all of H. They are linearly independent. So that set is a basis for H. Okay. So this gives us a bit of an algorithm for finding a basis of a set. If we have spanning vectors for the set, a set of vectors that span the set, all we have to do is keep dropping them out one at a time, dropping out a vector that is a linear combination of the others, drop them out one at a time until we've got a linearly independent set. And also, note that our previous theorem says that we can just start with the last one. Start with VP. Is it a linear combination of the others? You can start with that and just work your way down and try them all to drop one out. So now there are some special spaces that we've seen. We've already talked about the column space and the null space. We're going to introduce another thing here called a row space. But we're going to look a little bit more closely at the column space and a row space of a matrix. So for example, find a basis for this column space. How do we do that? Well, we're looking for, what's our space? Our space, H that we're interested in, is the span of these 3 vectors. Now the question is, are these linearly independent? Are they linearly independent vectors? Well, the answer is, how do we find that out? We do row reductions. We've already seen to find out if it is linearly independent, we do row reductions. So we put the basis, or we start with our matrix, and we row reduce. We're going to take row 1 minus 2, we're going to do 2 row 1 minus 3 row 2 is the new row 1. So now note that one of the things I'm doing here is I'm actually combining a couple of elementary row operations into one operation. So that gives us a new row 1, which is all zeros. Now, row reduced echelon form actually says you're supposed to put all the zeros on the bottom. So I'm going to do row 1 interchange with row 3 just to technically put it on the bottom. And then I am going to, actually at this point, that's all that I have to do. I didn't even have to do that last step. At this point, you can see that we have two non-zero rows. What we were trying to do here was show if these vectors are linearly independent. As soon as I get, when you have the square matrix, as soon as you get a row of zeros, you know that they are not linearly independent. So a row of zeros means the vectors are linearly dependent. Okay. So now the question is, which one can be built from the others? So let's continue our, so we need to remove a vector that is a linear combination of the others. So the question is, which one is that? So let's continue with it. Let's do another row reduction. So 2 row 1 minus row 2 is the new row 2. We get 0, 2, 0, and all zeros. And then we'll just do one more. So 2 row 1 minus 3 row 2 is the new row 1. It's going to give us that. So what do we get? We get that row 3 is a linear combination of the first two. So this shows that R3 is a linear combination, vector 3 is a linear combination of vector 1 and vector 2. So that means the basis is those first two vectors. And we can say that right up front because we can see that they are linearly independent. So those first two vectors are your basis. We've dropped out a vector that we can build from the others. What we're left with is linearly independent set. That means we already have our basis. And that leads us to theorem 6, that the pivot columns of a matrix form the basis for the column space. We've already seen this idea, but theorem 6 gives us the statement of it, that if you want to find out what vectors are a basis for your column space, take the columns that are pivot columns from your original matrix. Not from your new matrix, but from your original matrix. So what's the proof? Okay, so here's a rough sketch of the proof of this. You take A and you row reduce it. So you go through a whole bunch of steps, you come to B, which is the reduced echelon form. When you're in B, you can easily see that all the pivot columns of B are linearly independent. Okay. Why is that? Well, think about what it means to be a pivot column and how you could possibly create a pivot column from the other pivot columns, and you see you can't do it. Okay, so give some thought to that. Make sure that you understand that. But now A is row equivalent to B, so that means the pivot columns of A are linearly independent as well. Okay, and why is that? Think about how you got from A to B, and consider if you had a matrix that was just those pivot columns and you row reduced it, what would you get? You would get a matrix where every column would be a pivot column, which means that it's linearly independent. Okay. So if you don't see where that is, give it some thought and think about, well, if I take my basis, my matrix A, get rid of all the non-pivot columns in it, what am I going to get when I row reduce, and what does that mean? So also similarly, it means that the non-pivot columns of A are linear combinations of the pivot columns. Again, if you don't see this immediately, think about why this is. Think about taking your pivot columns from A, forming a matrix with that, and add one more column, which is one of your non-pivot columns. Row reduce it, and what does that mean? What does that row reduction tell you? Okay, so by theorem 5, that means all of those non-pivot columns, you can throw them out. And that leaves the pivot columns. The pivot columns are going to span the same thing, and they're going to be linearly independent. That is a basis. So your pivot columns form your basis. Now we're going to talk about a row space. This is a new idea. We've seen the column space. We've seen the null space, which we didn't talk about the null space again here, but we spent quite a bit of time on the null space before. And we've seen how to generate a basis for the null space already. Now we've seen how to generate a basis for the column space. What's a row space? Well, the row space of a matrix is the span of its rows. So you take a matrix, take each of the rows, and kind of turn them into vertical vectors. And the row space is, oh, this should actually be the span of those vectors. So everything you can build from those vectors made up of the rows. Very similar to the column space, just you're taking the rows. If you think about it, the column space or the row space of a matrix is the column space of the transpose of the matrix. Okay. So theorem 7 says if we have two matrices that are row equivalent, then their row spaces are the same. In other words, if you do elementary row operations to one matrix, you get a new matrix. The row space of both of those are the same. If that resulting matrix is in echelon form, then the non-zero rows of B form a basis for the row space, and they also form a basis for the row space of your original row space. So here's an example. Now we're going to see what all of these things together do. This is an example, and I've given you both the original matrix and the row reduced matrix. What's the row space of A, and what's the column space of A, or what a basis for them, and what's a basis for the null space? So let's start with the row space. What's the row space? To find the row space, it says you take all of the pivot rows. And this one says you can take them in either your starting matrix or your finishing matrix. So what are your pivot entries? Your pivot entries are those three. So if we want to get the row space of A, or a basis for it, you just take those rows from your original matrix, or from your reduced matrix, and use those. 1, 0, 0, minus 4 over 3, and 7 over 3, and so on for each of the three matrices, or three rows. And that is the basis of the row space. So you take the rows from your row reduced, that's the easiest way to do it, from the row reduced version, and that gives you the span of your original matrix, and they are guaranteed to be linearly independent. What about the column space? So we're looking for a basis of the column space of A. What's our rule for that? It says take the pivot columns from your original matrix. So it's columns 1, 2, and 3. So you take columns 1, 2, and 3 from your original matrix. And there is the basis for the column space. Okay. So remember, when you're taking the basis for the row space, you take it from your row reduced. When you're taking the basis for the column space, you take it from your original matrix. Now that leaves the null space. So for the null space, we're going to give each of these columns, 2, 3, we're going to give each of these columns a variable. Because remember, this isn't an augmented matrix. This is just the matrix of the matrix itself, and we're looking for the null space. So this is the equivalent of the equations x1 minus 4 over 3 x4 plus 7 over 3 x5 equals 0, and so on down the row, or down the matrix. And then we have our third equation, and our bottom row actually is all zeros, so we can ignore it. But that's our starting equations. Then we can rewrite these in terms of, so that we get an expression for each one. So x1 is equal to 4 over 3 x4 minus 7 over 3 x5, and so on down the list. And again, we have our free variables at the end, and just to make sure I don't forget them, I like to write them down as simple equations like that. Then what do we have? We have the null space of our matrix is equal to, we have the two free variables, so it's equal to x4 times something plus x5 times something. What are those things? Just pull out the x4s and x5s from each of those equations. 4 over 3, negative 2 over 3, negative 1 over 3, 1 and 0. And for the second one, it's negative 7 over 3, 2 over 3, 1 over 3, 0, and 1. That's the expression for our null space. So that gives us our basis for the null space. The basis is the two vectors that we have in these equations. And there is the basis for our null space. So again, these are three subspaces, or three vector spaces, that are often of interest. To find the column space, you take the pivot rows of your row-reduced matrix. To find the row space, you take to find the row space, you take the rows of your row-reduced matrix. To find the column space, you take the pivot columns of your original matrix. To find the null space, you make your equations and figure it out. Also note that here we have a 4 by 5. Your row space are 5-dimensional vectors. Your column space is 4-dimensional vectors. And your null space is, again, 5-dimensional vectors.